Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 3 on equivalent expressions. Now you've seen equivalent expressions before, but they're pretty important, so let's get right into it. Equivalent expressions. There's almost no more important idea in algebra than that of two or more algebraic expressions being equivalent. So let's first just kind of get into what equivalent expressions are. Two algebraic expressions are called equivalent if for every value of the input variable or variables, the two expressions have equal values. Equivalent expressions can always substitute for one another in algebraic manipulations such as solving equations or writing equations in different forms. So let's kind of discuss this, right? Often, when you're doing all sorts of things, whether it's factoring something or multiplying two binomials together or combining like terms, or even when you're solving equations and you're rearranging one side or rearranging the other side, you're really just producing equivalent expressions. And the important thing is, right, it's okay to sort of replace one expression with another one that's equivalent to it, because those two expressions are going to have the same value regardless of what value of x or y or t or whatever you put in. Now, equivalent expressions are produced by applying the properties of real numbers to the expressions. And this is the whole idea of algebra, right? The whole idea of algebra is to take properties that really apply to numbers and apply them to variables and expressions in the same way. So let's look at the major real number properties that we use in order to produce equivalent expressions. And there's really just three of them. So let's take a look at them. If A, B, and C represent three known or unknown real numbers, then the following are always true. Number one, the commutative properties of addition/multiplication. A plus B is equal to B plus A, and A times B is equal to B times A. And this is really critical. The idea that if I've got the sum of two numbers, right, 3 plus 4, x plus y, 7 plus negative 3, I can reverse that order and I'm going to get the same answer, all right? And the same is true for multiplication, all right? Now, by the way, for addition, it makes all the sense in the world. If I've got 3 cookies and I add 7 cookies, that's the same as if I have 7 cookies and I add 3 cookies. It's less obvious, right, when I have 3 times 7 and 7 times 3, right? If I have 3 7s, it's not, to me, completely obvious that that should be the same as 7 3s. And yet, if you set up an area array or something like that with rows and columns and whatnot, you can easily prove that multiplication is also commutative, all right? Now let's talk about number 2, the associative property of addition and multiplication. Now these two have to do with what happens when you add 3 numbers together or multiply 3 numbers together, right? And people a lot of times think, oh, this is the one that has to do with parentheses. Nah, it basically is this, right? If I have A plus B plus C, and in that first thing, right, and let's kind of break out here so I can point to things, right? If I have A plus B plus C, this implies that I should have the B plus C first and then add it to A. Well, I can also add A and B first and then add C. And again, that should be obvious. In other words, if I'm adding 3 numbers together, it doesn't matter which 2 I add together first. And the same is also true for multiplication. And again, it's less obvious why that particular fact is true, but it is true. In other words, if I multiply 3 numbers together, I can multiply these 2 together first or these 2 together first, and it doesn't matter. I could also multiply the first one and the last one together first, but that would actually involve employing the commutative property so that I could flip that multiplication. Now, the final property is one that we don't quite use as often, in sort of like the real world, so to speak, but it is still very important. Let's take a look at number 3. The distributive property of multiplication and division over addition and subtraction. In other words, let's now break out a little bit. If I have A multiplying B plus or minus C, I can first multiply A by B, then A by C, and either add or subtract depending on what's going on inside of this parentheses, or adding and subtracting. Now, you think about the distributive property with multiplication all the time, but it also works with division. In other words, if I have A plus or minus B all divided by C, I can first divide A by C, then divide b by c and add or subtract again, depending on whether I'm adding or subtracting up here. The multiplication distributes over the addition or the subtraction, as does the division. It also distributes over the multiplication or addition. Or distributes over the addition or the subtraction. Trust me, division does not distribute over multiplication. Now, let's take a look at how these properties get involved when we're creating an equivalent expression. Exercise number 1. When the binomial 3x plus 7 is added to the binomial 2x plus 3, the sum can be written equivalently as the expression 5 times the quantity x plus 2. Letter A asks us to test this equivalency with x equals -1 and x equals 2. Show your numerical work below. Okay, in other words, right, I claim that when you add 3x plus 7 to 2x plus 3, that sum is equivalent to simply the expression 5 times the quantity x plus 2. And what that means for them to be equivalent is if I take x equals -1 and I substitute it in here, and I substitute it in here, and then I add the two results together, I will get exactly what I would get is if I took just -1 and substituted it in here. So let's show that for x equals -1, and then I'll have you do it for x equals 2 by yourself. So for x equals -1, all right, maybe just do that. First, let's do 3 times -1 plus 7, which is -3 plus 7, which is equal to 4, right? Now let's do 2 times -1 plus 3, which is going to be -2 plus 3, which is 1, all right? And if I add these two together, I obviously get 5. Now, if I take a look and I substitute -1 into this expression, right? So I'll get 5 times -1 plus 2. That's going to be 5 times 1. That's also equal to 5. Now that doesn't prove that they're equivalent. It just really proves that, hey, if I substitute -1 in here and -1 here and I add the results that I get exactly the same thing as if I had put -1 up in here. But that could be an isolated case, right? For them to be equivalent, they'd have to be equivalent for any value of x I put in. So why don't you try the same thing with x equals -2 and see if you get the same result. Now, by the same result, I don't mean that you're going to get 5 again. I mean you're going to get whatever you got when you add these two expression values to whatever you got when you substitute it in here. This time we don't have to deal with any negatives, which is kind of nice, right? For x equals 2, if I substitute it into my first expression, 3 times 2 plus 7 is 6 plus 7 is 13. Then I have 2 times 2 plus 3. That's going to be 4 plus 3. That's equal to 7. And if I add those together, I'm going to get 20. Now let's see if we also get 20 when we put 2 into this expression. All right, we get 5 times 2 plus 2. That's 5 times 4. That's also 20. All right. And again, what equivalency means is if you gave me any number, it could be positive, negative, 0, irrational, rational, anything. It could be x equals 2,145.7. If I put it into here, I put it into here, evaluate, add the answers, I'm going to get exactly the same value as if I put it in here. And of course, right, maybe part of the point of equivalent expressions is I might rather deal with this expression than deal with these two together because it's just simply simpler. All right, now let's see why they are equivalent by using real number properties. Let's take a look at letter B. Show that the expression 3x plus 7 plus the expression 2x plus 3 is equivalent to 5 times the expression x plus 2. Justify each step you make with one of the real number properties. All right, well, let's see how we can get from here to here and justify every step along the way using a real number property. Let's do this one together. All right, so first things first, I'm going to put down this expression. Whoops, I'm going to try to put down this expression. Now, according to order of operations, that 3x plus 7 should be, should be evaluated first, and then the 2x plus 3 second, and then I should be adding them together. But I can actually rewrite this as 3x plus 7 plus 2x plus 3, right? So, in other words, I can regroup this addition, and I really have the sum of 4 different terms, but I'm going to regroup it so I'm adding sort of these 2 terms like that. Now, that's associative property. Whoops. Associative. And I'm just barely going to be able to fit it in there, right? So in other words, I'm going to group the addition of these 4 terms in this way. All right, now what I'd really kind of like to be able to do is sort of get it so that that 3x and that 2x are sort of closer to each other, right? Because technically speaking, what this expression says I should do is add 2x to 7, and then eventually add it to 3x, and then add 3 at the end. But I can actually rewrite this now by simply flipping the order here. So instead of 7 plus 2x, I can write it as 2x plus 7. All right. Now that's the commutative property of addition, right? So commutative property of addition. Okay. Now again, though, technically speaking, according to order of operations, I should be adding these 2 first, because I do what's in parentheses first. Then I should add it to 3x, and then I should add the 3 on at the end. But I'd like to regroup this at this point to make it like this. Whoops, not like that. To make it like 3x plus 2x plus 7 plus 3. All right. Now again, that is just regrouping because I've got the sum of 4 terms. I've now decided, well, actually I'd like to add these 2 and then add them together. And that is again associative. All right. Now, I'm just going to add the 2x and the 3x and get 5x and the 7 and the 3 and get 10. And there's really no property I'm going to use to justify that particularly except for just, hey, I added. All right. Now remember, I'm eventually looking to justify the fact that this is 5 times x plus 2. But keep in mind that this is 5 times x plus 5 times 2. So I can write this as 5 times x plus 2. And that's actually using the distributive property. Now you might say, well, that's not using the distributive property. The distributive property goes in this direction. In other words, 5 times x plus 2 is 5 times x plus 5 times 2. But equality is a two-way road. So in other words, if I've got a times b plus c is equal to a times b plus a times c, right? Equality is a two-way road. So in this case, what I'm doing is I'm not going in this direction, I'm going in this direction. All right. Now that is a lot of work to go from here all the way down here. All right. And oftentimes students get very good at combining like terms and doing other things like that without going through all of these different properties, right? They just sort of quote, know how to do it. But keep in mind that being able to do it really is employing all of these different real number properties, even if we're not thinking about them, even if we don't know what their names are. And I'll admit, right, commutative, associative, distributive. Distributive is actually the one that people tend to know the name of the best because they're distributing the multiplication. They're giving it to each part of the sum or the subtraction, right, or the difference. Associative and commutative, those are a little bit harder to kind of remember. Anyway, let's keep working with equivalent expressions. Let's talk about like terms. One common manipulation, in fact, I did it in the last problem and kind of brushed it off. One common manipulation to produce equivalent expressions is the combining of like terms. So let's talk about what a like term is because it's been a little while since you've talked about like terms. 2 algebraic terms are called like terms if they contain the same variable or variables raised to the same powers. For example, negative 4x to the third and 10x to the third are like terms. And they're like terms because they both contain an x and that x is raised to the third power. But 5x squared and 2y squared are not like terms. All right. The point is like terms can be combined. Now the reason 5x squared and 2y squared aren't like terms is not because the powers are different, but because the variables are different. The real key, though, is that like terms are important because you can combine them. It's like saying, well, I've got like 2 llamas and 5 llamas, I've got 7 llamas, right? But if I had 2 llamas and 5 cats, I don't have 7 llama cats, right? I don't even know what a llama cat would be, but it would definitely be a very angry animal, and it would likely spit a lot. Let's take a look at exercise number 2. Rewrite each expression below in an equivalent form by combining all like terms. Replace subtraction with addition of opposites if needed. All right. Now, again, I'm going to go through kind of a rigorous process to come up with the final answers here. Well, a semi-rigorous process. All right. But I want to point out that we really are employing all sorts of different real number properties. So let's take a look at letter A together. All right. We've got 3x plus 8y plus 5y minus 2x. Now, right, technically, we'd have to use a bunch of commutative, associative, and believe it or not, a little distributive property in this to get to our final answer. But ultimately, the way that we might want to think about this is 3x plus 8y plus 5y plus negative 2x. And the reason I only want to think about it that way is because addition we can rearrange using the commutative and the associative properties so that I have 3x plus negative 2x plus 8y plus 5y. All right, 3x plus negative 2x will give us just a single 1x, and you can put the 1 in front of it, most people won't, and 8y plus 5y will give me 13y's. Now, don't get me wrong. A lot of students will get good enough, especially at the Algebra 2 level, to say, well, I have 3x minus 2x, that's 1x, and I've got 8y plus 5y, and that's 13y, and that's fine, all right? But technically speaking, this is really what you're doing. You're changing that subtraction into an addition by the opposite, right? Subtracting 2x is the same as adding negative 2x, and then you're really using both the commutative and the associative properties of addition in order to rearrange the expression to look like this, and then you're just combining like terms by combining the coefficients, the numbers that are multiplying the variables, to get the final coefficient. Let's take a look at letter B together, and then we'll have you do letter C on your own. Letter B says 5x squared plus 8x minus 4 minus 2x squared minus 3x plus 10. All right, and again, I'm gonna kind of go through this quote rigorously. Right? In this situation, we've got 5x squared plus 8x plus negative 4 plus negative 2x squared. Now I'm not going to have enough room. Plus negative 3x plus 10. All right? And again, the reason that I do this is so that I can do all this kind of rearranging and get 5x squared plus negative 2x squared. Lots of parentheses used here. Plus 8x plus negative 3x plus negative 4 plus 10. All right. 5x squared plus negative 2x squared will give me a positive 3x squared. 8x plus negative 3x will give me a positive 5x. And negative 4 plus 10 will give me a positive 6. All right. Now again, I encourage you to be able to look at this and go, well, 5x squared negative 2x squared is positive 3x squared. 8x minus 3x is 5x. Negative 4 plus 10 is positive 6. Completely okay. Why don't you go ahead and see if you can combine like terms in letter C. All right. Well, let's see if we can do it without doing all of this parentheses work and things like that. We always want to start with the highest power first. That's negative 5t squared plus positive 2t squared. That's going to leave me with a negative 3t squared. The next power down is just t to the first, and there's only one of those. It's just 8t, so there's nothing I have to do with that. There's nothing I can combine. And then I have a positive 10 and a negative 1, and when those combine, I get a positive 9. So negative 3t squared plus 8t plus 9. All right. Combining like terms is one of the most important things, not most important, sorry, is one of the most common things that you end up doing in Algebra 2, and you want to get good enough at it that it's sort of a no-brainer. All right. Now let's talk about breaking apart expressions. it's important to note that just as we can write equivalent expressions by combining like terms, we can also write equivalent expressions by breaking expressions apart. All right? Now, this is important because a lot of times people kind of think, all right, yeah, I've got this expression plus this expression, and what they're telling me is I got to like combine them all, combine like terms, et cetera, to get some final expression. But sometimes in math, we want to be able to take an expression and kind of break it apart, right? And that's okay, because again, equality is a two-way street. It's not a one-way street. It's a two-way street. So let's take a look at some problems that kind of get at this idea in a novel way, and you may remember these from Algebra 1. Exercise number 3. The expression x plus 3 is equal to -7 for some value of x. And I don't want you to think about what value of x, just equal to -3 for some equal to -7 for some value of x. Use real number properties to determine the value of the expression 2x plus 16 for the same value of x. Show the manipulations you use. Now don't get me wrong. You could totally figure out what the value of x is and then plug it into this expression, but that would kind of completely miss the point. All right, so let's think about what the point is here, right? I want to take 2x plus 16 and I want to kind of manipulate it some so that I can get an x plus 3 in there. All right, well, think about this for a moment. 2 times x plus 3, I'm just going to put this over here. 2 times x plus 3 using the distributive property is 2x plus 6. All right. So I could take this expression and I could rewrite it as 2x plus 6 plus 10, right? All I'm doing there is I'm taking 16 and I'm breaking it into 6 plus 10, okay? I'm uncombining the 6 and the 10. But then, of course, I could take 2x plus 6 and I could write it as 2 times x plus 3 plus 10. All right, now I still don't know what the value of x is, but I do know that x plus 3 is equal to -7. So I could now say that this is 2 times -7 plus 10. That's -14 plus 10. And that's -4. All right. Now it's kind of interesting because again, here I'm sort of running the addition backwards, right? And I'm really kind of doing something interesting, which is that I'm sort of, suddenly grouping these two together. So I'm using the associative property of addition almost backwards. Then I'm using the distributive property sort of backwards, i.e. factoring. We'll talk about that more in the next lesson. And then I finally have that expression that I was looking for right here so that I could substitute -7 in for x plus 3. Let's play around with exercise 4 in the same way. The expression n plus 5 is equal to 2 for some value of n. What is the value of the expression 3n plus 15 times n plus 7 for the same value of n? All right, what I'd like you to do is play around with this one and see if you can figure out what that's equal to. Well, the real question is, how does n plus 5 relate to 3n plus 15? And how does n plus 5 relate to n plus 7? All right. Well, one thing I could note right away is that 3 times n plus 5 is equal to 3n plus 15. All right. So that is certainly true. I could also note that n plus 5 plus 2 is equal to n plus 7. All right. And so what I'm seeing is I'm seeing that n plus 5, and maybe even I'll put a parentheses around this, right? I'm seeing that n plus 5 in both this expression and this one. So I can rewrite this expression into the following. That's 3 times n plus 5 times n plus 5 plus 2. All right, so I'm just replacing 3n plus 15 with 3 times n plus 5 and n plus 7 with n plus 5 plus 2. But now I know n plus 5 is equal to 2. And one of the major principles in mathematics is that equals can substitute for equals. All right, it's called the substitution property of equality. But it's also just obvious. Equals can substitute for equals. So this parentheses now is simply 3 times, 3 times 2. And this parentheses is 2 plus 2, right? All I'm doing is substituting 2 in for n plus 5, and that's going to now be 6 times 4, and that entire expression would be equal to 24. And the cool thing is you really, in this problem and the last problem, could figure out the value of n. For example, in this problem, if n plus 5 is equal to 2, then n would have to be equal to negative 3. And you could literally then take negative 3 and substitute it in here, and find the product, and you'd find it was equal to 24. It would defeat the purpose of the problem, but you could actually check your answer. All right, let's keep going. Infinite equivalent expressions. Any algebraic expression can be written in an infinite number of ways that are equivalent. Which form you write an expression in is largely due to what you're trying to determine from it. All right? And again, that's critical because a lot of students think, oh, okay, I see this expression and this expression. Oh, I'm supposed to add them or multiply them or do whatever the problem looks like it's telling me to do. And often the problem does tell you exactly what it wants you to do. All right? But sometimes you have to think about what the problem is getting at, how to manipulate the expression specifically to achieve a given purpose. So let's take a look at exercise number 5, our last exercise. Using properties of real numbers, rewrite the expression 8x plus 12 in at least 5 different equivalent ways. And again, there's an infinite number of ways to do this, so 5 is barely scratching the surface. But let me give you an example, right? Here's an example. I could rewrite 8x plus 12 as, let's say, 4x plus 4x plus 12. That is an equivalent way of writing 8x plus 12. I've just broken it up, right? Here's another equivalent way of doing it, right? I could write 8x plus 12 as 2 times 4x plus 6. That's another equivalent way of writing it. Why don't you pause the video now and play around and see if you can find additional ways of writing it. Well, how about this? How about 8x plus 12 is equal to 8x plus 8 plus 4. Maybe I'll take that 12 and break it up, right? Or maybe I want to do a little bit more of this kind of stuff, and I could say 8x plus 12 is equal to 4 times 2x plus 3. All right. Maybe I want to break up both the 8x and the 12. Maybe I want to say, well, 8x plus 12 is equal to 6x plus 2x plus 10 plus 2. That would also be an equivalent way of doing it. I mean, really, you could even say this. You could say 8x plus 12 is equal to 12 plus 8x. That's not the most imaginative way of doing it. All I'm doing is applying the commutative property of addition, but it would certainly be a correct equivalent way. So there are lots and lots of different ways to write an expression as an equivalent expression by using those 3 major properties of real numbers and addition and subtraction. All right? Addition, multiplication, subtraction, and division. I mean, hey, we didn't even get the division one in there. How about this one? How about 8x plus 12 is 16x plus 24 divided by 2. Right? That would also be an equivalent expression because that division would divide into both of those, right, and give me the 8x plus 12. The point is we can rewrite lots of expressions in different ways that are equivalent depending on what we're trying to achieve, and we'll see that throughout the course. So, let's summarize. All right. Today we talked about equivalent expressions, an amazingly important idea. This idea that we can take an algebraic expression, something that has variables in it, right, and we can rewrite it in a way that gives us another expression, an expression that looks different, you know, maybe radically different or maybe just slightly different, but in a way that is algebraically equivalent, meaning that if I took the same value of x and I put it in both expressions, they would return the same output value. This is a critical idea. It comes up when we manipulate functions, when we solve equations, when we rearrange expressions. It comes up all the time, and it's important to understand that when you do these things, all you're doing is taking rules that apply to normal everyday numbers and then applying them to expressions in order to rewrite them. All right, we'll see this a lot obviously as we go forward. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.